Swayam Prabha. Digital India. Educated India.
Welcome to the class of high performance computing for scientists and engineers, and we have already discovered two modules of this course. The first module was on fundamentals of parallel computing, and in the second module we have discussed about OpenMP programming, which is a programming paradigm for shared memory parallel processors. And now we will look into distributed memory parallel programming, and this is the third module in which we will start discussing about message passing interface, which is an API which is heavily used for distributed memory parallel computing. And this is the first lecture, which is 19th lecture of this course. This lecture will discuss about introduction to MPI and distributed memory parallel programming. So we will cover shared and distributed memory computing, some fundamentals about them. We have already discussed about shared and distributed memory computing, but we will again try to compare these two methodologies or these two models, mostly due to the fact that on shared memory programming we have already built a foundation. So now what are the difference of shared memory programming and distributed memory programming we will discuss, and from there we will pick up our voyage on distributed memory computing. And then we will discuss about message passing, which is the probably most demarcating pointer of distributed memory computing model, and the API for message passing, which is universally used, is message passing interface or MPI. We will introduce MPI at that point of time, discuss about some basic function calls. We will see what is a communicator on MPI, how do we identify the CPUs or the computers which are participating in an MPI job, and how do we give their identity during the program. So we will discuss that while discussing communicator in MPI program, and then we will see our first MPI program, which is Hello World program. If you remember, for OpenMP also we started with Hello World program. That means there are multiple processors and each processor will independently write Hello World while executing the same MPI program or same parallel program. For OpenMP we have done that, here we will do it for MPI. This is the this will cover the introduction to MPI and message passing based distributed memory computing. And with this background, in the subsequent lectures we will discuss about data transfer protocols in MPI, and how we will see how to write scientific computing algorithm in a parallel MPI version. We will do these things in follow-up lectures. So this lecture and the next lecture will be devoted on giving you introduction to MPI and distributed memory computing. So when we work on a parallel program, what we ask that there are multiple processors and each processor will do some part of work, and these processors will work in parallel. That's why we call it parallel program. So there will be some concurrency in the job, and each of the processor will take care of one of the tasks, and these tasks are concurrent tasks. So however, because they belong to a same problem, so there is some requirement of communication across the processors, because they are trying to solve the same problem. We have seen in shared memory computing that they write to common address space, and whatever each processor is doing, after one parallel construct, we need to consider the output of each of the processors calculations and combine them or do something with them. We have seen it many times in different OpenMP applications. So there is an there is a requirement of sharing data or sharing the same data space or sending information across the processors. Now, if we see shared memory, we have discussed it earlier also. It's like there are few concurrent instructions, and each of the processor is taking care of one. However, in shared memory, the entire data set is visible to all the processors, like 4 people sitting on a table and they have to solve some puzzle together. So the concurrent parts they can take care of in parallel. In a distributed memory, so this is a shared memory system. In a distributed memory system, there are different processors and each have their own local data. So they are working on the local part of the puzzle. Given a puzzle to 4 different people, they are sitting at different tables and working on the local part. However, it's in a grand, it's a complete single puzzle. So they need to communicate across themselves, and there is a network switch. So this will write a network switch. There is a network switch through which all the computers are connected, and through the network switch this computer can send some information to this computer, it can receive some information from this computer, so on. So they can share data, they can get some information some of the other computers, so on. So this is a distributed memory model. The third one, which will actually not discuss over this course, but which is I'll say which gives us a route to very large scale supercomputing exercises, is a hybrid model where there are different shared memory processors, the different symmetric multiprocessors or different shared memory computers, where there is a single memory shared by multiple processors, and these different shared memory processors with their different local address space, local data set is connected to each other, again via something like a network switch. So it's a, and all the HPC, modern HPC clusters, all the hybrid architecture CPU systems, they are like this, that there are different shared memory units which are connected to each other via a switch. So the advantage is that you get the shared memory computing. Also, you can distribute different parts, like large parts of the computing, to different units, and you can see a distributed memory computing among these parts. So distributed memory computing, and each of the distributed memory part is again further parallelized by the shared memory machines. So this is called a hybrid architecture. And there is also another cutting edge model, which is a CPU GPU model, that there a CPU which gets the whole problem. This CPU is connected to a GPU which has multiple small processing units, and GPU has also its own data set. So the main data which belongs to the CPU, part of the data is copied to the GPU on which these multiple processors will work. So these processors will work on this data, because there are a number of processors, each can take care of small part of the data, and then they will give the output back to the CPU system. This is a CPU GPU architecture. GPUs cannot work independently, if standalone. If you ask the GPUs are accessories, so if you ask the programmer to directly work on the GPU, it is very difficult, especially for scientific computing community. They rely on a CPU, gives the entire job to the CPU. CPU distributes the job into small memory pieces and small instructions, and asks GPU to take care of that. So it's both copying memory as well as copying the main instructions, or the concurrent, or sending the concurrent instructions to the GPU cores is important. So in to be more specific, there are basically two types of programming model in parallel programming, and which are shared memory programming model and distributed programming model. And what we discussed about hybrid programming model is a combination of both shared and distributed memory. GPU also works in a shared memory model. We can see that the data space or address space which is copied to the GPU memory is visible to all the GPU cores. So, in shared memory programming model, all the processors can see whole of the memory that is available, or the entire memory is a single shared address space and multiple processors are connected to that. So, each processor can see any part of the memory, and all of our multi-core systems, like if we buy a dual core laptop or quad core laptop, it is basically a shared memory system. In distributed memory model, or in shared memory, we can see that there is a common address space which is, let's go to the pointer. There is a common address space in which multiple processors are connected. So, whatever they are working on the common address space variable. The distributed memory programming has a difference that the processors can see limited part of the memory, and so the entire memory space is not visible to the processors. Each processor can see a limited part of the memory, and it can, one CPU can only access to that memory and alter it the local variables. It cannot see entire memory or cannot do anything. So whatever tasks are given to the processor, that must work on the local data or the local RAM of that particular processor. It cannot go to a remote memory and work there. If it needs to get anything from the remote memory, it has to be done through the network cable, through the data transfer or message passing. So, multiple CPUs with their own local memory are connected via network cable. This is the distributed memory programming model. Therefore, we can very easily understand that there will be differences in the programming approach also. So, here we look into a same memory, and we have seen that in OpenMP it is a very similar, a same for loop which is operating over a data set, and we just write OpenMP construct that part of the iterations are given to a processor as sum of the threads, and different threads can work in parallel if there is no dependency among them. But a distributed memory programming will be of course different. We have to identify this piece of data and give it to the processor, and this processor only sees this data. So, the whole problem has a global reference, but when a processor looks into the problem, its viewpoint is very local. It cannot look into the global problem. Any of the processor can only look into its own local memory. None of the processor can look into the whole memory here. So, some definitions are important here. One is process. Process is executing instance of program. It has distinct address space. It is different from other executing instance of the program in a way that it has separate resources. So, one particular instance which is being executed by a program which works on its own distinct address space is known as process. We can also tell that in a distributed memory system, each processor is executing a process. We usually do not mention processor here, rather we take it as a process, because there can be some hybrid architecture when one processor is executing multiple processes, or some way there can be co-processors there. So, processor is little confused. The word processor is little confusing here. Processors can, even multiple processors can point to the same address space, but process is a very distinct term used in parallel computing. A process means an executing instance of the program which works on its local data, which works on its distinct address space. This executing instance does not share its address space with any other executing instance. There can be multiple processes running for the same program, but each of the process has its own memory space. Thread is a different concept, we have looked into threads, that multiple instances are working on, multiple instructions are being operated on, however, they point to the same address space. So, the entire group of threads which is pointing to that address space are part of the process. So, we can call thread is the subset of the process. A process has its own address space, it's executing instance of the program which has its own address space. A thread is a process, something like a process which share, or something like an executing instance of the program which share its resources, which shares its address space with some other threads. So, when on the same address multiple instructions are going, these are threads. When different an instruction is going only on the particular distinct address space, if there are multiple instructions, there are multiple address spaces, this instruction instance is process. So, thread is what we have looked into shared memory program. Threads have to be part of a process. There is a whatever the instructions or instances going on are being executed over a particular address space, that executing instance is a process. Inside a process there can be multiple threads, that many sub instructions which are executed concurrently on the same address space. So, threads are subsets of processes which has its own address space and one executing instance. The program going through part of the program which is working through the same address space is a process. The inside the process, if there are multiple instructions but they are using the same memory space, they are threads. So, threads are part of the process. Threads cannot be launched independently. We have discussed about threads in shared memory programs. When the group of threads they are launched in parallel in a shared memory, when we launch this group of threads, this is the parallel part of the shared memory program. So, in parallel we launch a group of threads, they execute concurrent instructions using the same shared memory. But in distributed computing we will not talk about threads because we are not sharing the same memory space. We will talk about processes which has their own distinct memory space. In distributed memory program, number of independent processes execute instructions concurrently. In shared memory program, number of threads are being executed, they connect to the same global address space. In distributed memory program, number of independent processes are being executed, and each of the process by definition is connected to its own distinct address space. The advantages of shared memory programming is ease of programming. We have seen that in OpenMP programming, it's actually very easy. You only have to you have to know about basics of OpenMP program. You have to identify that region where concurrently instructions can be executed and write some OpenMP construct. You don't need to do anything about the memory because they are writing to the same memory space. Yes, you need to take care of the memory synchronization. So, if you see that there is some possibility of cache conflicts or contention, you have to write a proper OpenMP construct there, like critical or atomic or reduction. However, you really do not need to think about that which thread will go to will take care of which part of the iteration. Even if you have to take care of that, OpenMP has very simple clauses for that, or which part of the instruction it will be better to execute in which thread. Programmer doesn't really need to look for these things. This is something which OpenMP takes care of that. The load balancing, OpenMP itself can take care of that. At best you have certain control over it. Lower latency, because there is no requirement of sending data from one processor's memory to another processor's memory through a network cable. There is no requirement in that in OpenMP because it is the same data space which all the processors are using. So, it has lower latency, and this is data sharing is fast because it's again through something like a PCI bus. Processors are connected to the memory, and with the very first channel they are writing the memory, and it's also uniform because this is the same memory where all processors are sitting there. It's like the same table which is being shared by multiple people. So if I'm eating something here, everybody is dining on the same table. If I'm eating something here, this guy can directly see that this part is being eaten out. The disadvantages are that there is limited scalability between memory and CPU. So you really cannot bring many people to sit here. The space constant is there, the bandwidth constant is there. You really cannot increase the number of CPUs, or you really cannot increase the memory size. There are certain restrictions there. One of the big disadvantage is cache coherence protocol, false sharing, etc., which will add certain overhead. If you increase more CPUs, the traffic on the shared memory CPU path increases, that makes the program slower. So you cannot go up to thousands of CPUs in a shared memory system, or you just cannot take your laptop, which is a quad core system, and think that I'll put another CPU on that. There are certain restrictions on that. And if you need to use a synchronization construct, if you need to use atomic constant, if you want to see that this part will be executed in an order, one by one threads will do that. So any of the synchronization constructs, for any of the synchronization constructs, the programmer is responsible. It's not that the programming model or the algorithm itself takes care of the synchronization. You have to identify the part, or the compiler, it doesn't itself take care of the synchronization. You have to identify the location where synchronization is required, and you, as a programmer, you have to put a synchronization clause or a synchronization construct there, so that access to global memory is correct and without latency for different processors. So there is a programmer's job who needs to identify that this should be a critical access to the operation, this part. And in terms of increasing the, we discussed also earlier, in terms of increasing the size of the or in terms of increasing the resources, if we think of getting large number of processors, large memory, it is difficult. From the design point of view, from the manufacturing point of view, from the heat dissipation point of view, you really cannot keep on increasing processors there. There is a space constant, there is a heat dissipation constant, there is an electricity constant, there are many constants. So you really cannot go to a very large computing system here. You are restricted by, say, hundreds, few maximum, with a very high end parallel symmetric multiprocessor. You are restricted to few hundreds of processors. In NUMA, you can probably have more number of processors, but still these restrictions, some of these restrictions are there. So you really cannot scale up your resource. You really cannot increase your resource by adding processors or increasing the memory here. So there is some restriction on the resource in terms of hardware itself. If you have a very large job, you cannot use shared memory machine, because you will not be able to find out the right hardware which will provide you the large number of processors which are required to solve this job. Well, so on the other hand, and the biggest advantage is that we have OpenMP, which is a very simple library to learn, and we all had I mean, say 3 to 3.5 hours discussion on OpenMP, and I think any of you can now jump and take your code and make it OpenMP parallelized. So we have OpenMP, which makes it easy to work with the shared memory environment. Well, so in the distributed memory programming, there are multiple computers, each has their own own RAM and own local memory space in the RAM, and they are connected via network switch. The big advantage is that this is scalable. You can add more CPUs, each CPU will come with its own RAM, so there is no restriction by the CPU memory bandwidth or CPU memory channel width, you can increase as many as CPU, and each CPU will come its own rack. So only you need a network switch which has many ports, and you can connect it via network switch. So it's not restricted by the hardware, software, or neither by space or heat transfer issues, because these are basically you are connecting many computers, and they may not be physically located at the same space because they are connected by network switch. You can even use internet to connect them. So you can actually bring further more computers, each has their own RAM, and put it there. That gives us the biggest advantage of using distributed memory programming, that we can have a very large system. We can have very large scale, high resource with large number of processors, in which we can solve large problems. We can solve problems which will require many compute hours, because we can use quite higher number of processors compared to the shared memory system. This is the biggest advantage here. Less contention from private memory spaces, because none of the processors are trying to access the same memory element. There is no cache conflict. There is no requirement of using cache coherence protocol. So cache based issues are not there, and we will discuss this later, that today's high end computers, I am not talking about supercomputers, just computing units with CPU RAM cache triode, CPU RAM cache triode, these computers rely heavily on the cache based architectures, as well as the softwares, the compilers. They rely heavily on how CPUs will access cache and how memory will flow from cache to CPU, and how memory will be prefetched from RAM to cache. Now, if you are bound by cache coherence, many times you cannot take this advantage. Though the computer can perform very fast, but it gets significantly high overhead due to cache coherence and due to false sharing, or if you are putting something like a critical issue, you are not critical construct to avoid false sharing, which we have done for our OpenMP program. Many times you are not utilizing the best parallel performance of the system. But if you have a distributed memory system, there is no same address space which will be shared by multiple computers. So these cache related issues, cache conflict issues are not there, as well as the bandwidth issues while multiple computers are trying to write to the same memory location is also not there. So this is another significant advantage here. Also another advantage we will see, that as we have a large problem and we break it down to smaller memory problems, the small memory units are cheap to buy. You have to buy a 1 terabyte RAM and you have to buy many 4 gig RAMs. This 4 gig, you will see that you can save money if you just go for buying 4 gig RAMs only, because in terms of motherboard and other requirement, this is less expensive. So from the expenditure wise fact also, if you can break the problem into small memory units, in what you do in distributed memory system, that is advantageous. In distributed memory programming model, what is important is that as they are not writing to the same address space, however, all the processors are working to solve the same problem. Therefore, there is some data which is shared across the processors, which is common across the processors. And how this data sharing will be done? They are not sharing the data space. So we say we are not sharing the there are two persons who are not sharing their bank account. Rarely people share bank account unless they are close relatives. But I need to send money to you. So what I'll do? I'll do a bank transfer. I'll do an online transfer, or I'll give you cash. I'll do some transfer. So as they're not sharing the same address space, if they have to share some information, if they have to give some information to other, the processor will send this information to a remote processor. So the remote process, this can be on the same machine. In the same machine there are multiple computers. I can multiple processors, I can make separate address space for each of the processor and run it as a distributed memory program, or it can be a different remote machine. And this, while writing a distributed memory program, we have to be sure that this processes or these processors which say sending the data and which receiving the data, they both have to be on the same page, that the processor which sending the data should give the sending instruction and the receiving processor should be able to receive the data, accept the message. This is one important, very important step in distributed memory programming model, that they should be connected, the processes or the processors should be connected to each other. The processors that are being executed, they should have a route to send data from one to other. So, in essence, because one processor will send data, other will receive it. So, it is basically copying data from one's memory and it will go to another processor's memory. So, it is not like money that if I give it to you, I do not have that money. It is like it is information. So, there is a difference between money and information. I know something, I tell you, I do not forget it. But I have 50 rupees back, I give you, I have 50 rupees note, I give you, I do not have the 50 rupees back now. So, it is not physical thing, it is information. It is not material, it is information. So, if one processor gives the information, it still retains the information. Therefore, it is not giving it, it is not cut paste, it is copy paste. It is copying the data from one processor and putting it into the receiving processor. Unlike shared memory model, the programmer is responsible for movement of data between the processes. This is very, very important. In this shared memory, we have seen that we did not bother about sharing data between the processes. We did not even bother about writing local data and shared data. If we write anything as define anything in shared data, it is shared. So, there is how each of the processes or how each of the threads will know about certain change made by other thread. In OpenMP, it is shared memory variable. So, if one thread changes, other knows it. The programmer does not need to even worry about that. Programmer cannot even do something on that unless he only can define it as private, so that others cannot see it. How others will see, just declare it shared, everybody will see. But in distributed memory programming, programmer has to ensure that data moves from one processor and is copied to another processor. The movement of data at which instant, from which processor to which processor, which data will be moved, it is programmer's responsibility to specify it. In addition to the advantage of using many remote machines, MPI has another advantage, that it forces to divide the memory between processes. So, instead of using a large piece of memory, the memory is broken down into the main problem is broken down into small memory units, and each process is attached to one of the memory unit. The help is that each process is now working on a localized part of data. So, the problem is very much local on which each process is working. What is the advantage on that? That each one is working on a small data set. So, the cache miss type of issues, that the entire matrix, almost entire matrix can be copied into the cache miss type of things, and or the registers, they can use the issue of data localization. Data locality is very good for computer performance, for computational performance. So, it forces, because each process now works on a small memory unit, the processes are forced to work on the localized data. And moreover, in distributed memory programming model, which is good as well as a little difficult also, that the programmer has to think on a distributed memory paradigm. He shouldn't think about the global problem while writing the program. What matters to him is the local part of the program, which is being local part of the data, which is being accessed and operated by each of the processor. So, programmer looks from a local perspective on the data set and he also has to decide that which part of the data has to be moved and when to move that. So programmer gets more responsibility. The programmer's job is also a little more difficult in distributed memory programming model, because he needs to, instead of the global view which generally comes to us when we think of a problem, he now needs to look from a local perspective based on each processor, and then he also needs to think about which data has to be moved and when to move. So we can look into the essentials of the distributed memory programming here, and after that we will go look into message passing, which is the stem of distributed memory programming. That how many people are doing the work, degree of parallelism, and these are the aspects from the programmer's point of view one need to think about when writing a distributed memory program. How many people or how many processors are working on that? What is the degree of parallelism? What is needed to begin the work? That these need to identify which processors are working on that, need to initialize initialize an environment in between them so that they can communicate in between each other. And there is something else, or some other important issues also which have to be initialized. Who does what? The load distribution in OpenMP, who was doing load distribution? OpenMP itself, the compiler was doing load distribution. It is giving number of threads to allocating number of threads to number of processors. But in here, who does load distribution? Programmer has to take care of load distribution and ask one particular processor to work on that part of the data. Access to work part, or how will be the data access, how will be the IO access, that is again it has to be thought from a distributed memory perspective now. Whether the processors need any info from each other to finish their own job. What are the requirement of getting information or data from the other processor to finish its own job? What is the requirement of communication? When the communication will be done, and which data will be communicated? And when they are all done, they are like this shared memory, as multiple processors are working for the same problem, there are requirement of synchronization also. So when synchronization will be done, and what is required to collate the result. So there are certain pointers which we need to take care of when developing a distributed memory programming. And fortunately, we have an API which has been developed by number of people working in this area for very long time, almost for 3 decades. It's available to us, called message passing interface, which can take care of all these parts. Only we need to know about the library functions on this API, on message passing interface, use the wrapper to call the library functions, use a wrapper while compiling the program using MPI, and these parts will be taken care of. And in the subsequent lecture we will see about message passing, what is message passing and what are the features of message passing, and distributed memory programming. And we will also try to compare a distributed memory program with a shared memory program, and then we will look about message passing interface in detail. Thanks.